So what I would like to tell you is joint work with Mihailo in the audience, and I'll tell you a little bit how we got into this. One good thing of giving the lecture, a little bit later in the week is that quite a bit of a background has been given already, so I will save me a little bit of time. Let me begin a little bit by telling you the possible motivation of this. At the end of the day, it's not the only thing you might want to do, but let me begin telling you quickly about the Wells zeta function that has been mentioned already. We begin with X and a vector field on a closed manifold, and out of the closed orbits, you cook up a function, psi of r. One thing that I do that I have to sort of apologize, I seem to belong to the camp that uses 2 negative signs rather than 3. I'm not sure if that's a crime. So you pack all the periods of the primitive closed orbits, and you sort of take a product in that way, and then it's sort of clear that if the real part of S is large enough, then that product actually converges, and then it's a great, relatively recent result that this function can be meromorphically continued for all values S in the complex numbers. So I guess the sort of original proof is proved by 2 people in the audience here. And then there was a microlocal approach by Diatlov and Sporsky proving a sort of similar result. And I guess the point of view that I will take, maybe I'll tell you this right away, is the sort of microlocal point of view of the second paper. Okay, so that's great. So then, you sort of start looking at the value of this function at 0. You sort of have some sort of belief that that value or what happens around that value might carry some information related to the topology of the manifold or to something else, as I will try to describe. And at first I will be interested in the order of vanishing of this function at s equal to 0. So I call m of x, so x is an arbitrary Anosov flow, and I look at the order of vanishing of this function at s equal to 0, and by that I mean, let me just be a little bit precise, m of x is a unique integer such that s to the minus m of x times the Wells zeta function is a holomorphic function near 0, and at 0 has a non-zero value. So I call that quantity m of x. And the basic question is, what kind of information does this quantity carry? And as I mentioned before, we have already seen a little bit of this in some of the previous talks. And so as I will try to explain in a minute, the quantity is closely related actually to resonance spaces, but of distributions with values on the bundle of forms. Yeah? So we are going to be looking at the differential forms with distributions, and I will try to sort of make the point that we are not actually looking at all of them, but a sort of very special kind of sort of class. And this will be, the thing that will essentially command the actual behavior of this quantity. So the first result, as far as I am aware, in a general setting, so there are definitely results in the constant curvature, going back to Fried, using the cellular trace formula and so on. But the first thing that really somehow kind of amazing result is this paper by Diatlov and Sporsky in 2017, in which you take any metric of negative curvature, and then the order of vanishing at 0 for the Wells zeta function of the geodesic flow is actually minus the Euler characteristic of the surface. So I don't know, when I first saw this, I was sort of quite shocked. I mean, one thing that it tells you right away is that from the length of the closed orbits, you can tell the actual topology of the surface that you're on. So I don't think this was known before. I mean, maybe someone can correct me on this. So that is, I think, is quite sort of remarkable in itself. So we got very interested when this paper came out, and we started to kind of look, the paper by Dyatlov and Svorsky, goes very quickly. You can see that you can do something very similar in the contact case. This is really not, the proof kind of carry almost immediately to the contact case for a contact Anosov flows. And then my sort of, obvious question at the time is, what happens is the contact world is, very nice world that we all kind of inhabit and we are very comfortable with, but it's not really the only kind of possible Anosov flow you can look at. So the first, step out of that class would be to see, well, what about volume preserving Anosov flows? Do we still sort of capture the same thing? And one thing that we did with Mihailo a few years ago was to show that you can actually make volume preserving deformations of the geodesic vector field and make this order of vanishing at zero jump, sort of drop by one, by creating essentially the mechanism that creates this is that you kind of make your flow in such a way that the Lewin measure, which is actually preserved, develops a winding cycle. It creates a non-trivial class. I'll tell you a little bit about winding cycles in a minute. And if you look at this, it's a classical result that the Lewin measure for the geodesic flow or for any contact flow has always zero winding cycle. So basically, in the previous computation, they were not seeing the winding cycle because they were essentially restricting to a sort of very special class of flows. Okay, but now what Dyatlov and Svorsky wanted to do was to sort of, as I understand it from them, at first they thought that this would actually not be constant, and then they went and did the computation in dimension 2, and they realized that it was actually constant, the same for all metrics. Now it turns out that if you go one dimension higher, this thing also jumps, but not just within the class of volume preserving Anosov flows, but within Riemannian metrics, and not just within Riemannian metrics, but within the conformal class of the Riemannian metric. Yeah? So you can begin with the hyperbolic metric, and then what we prove is that essentially generic conformal perturbation of the hyperbolic metric will produce a jump in MOX. Okay, so at this point I kind of really tell you kind of meta principle, which I think holds true, right? Essentially what is sort of happening in this kind of scenarios is that whenever you move from a sort of, good world, let's say the sort of contact world, where you have a lot of additional structure, your resonant forms have a sort of certain size. As you sort of go out of that in a slightly more generic situation, you would expect the space of forms to kind of shrink a little bit. Yeah? And then that would expect to produce some sort of jump in the real zeta function. And that very same principle is actually what operates here. So the hyperbolic metric has a lot of additional symmetries from the point of view sort of invariant objects by the geodesic flow. In fact, it's kind of well known that the space of sort of invariant two forms for the geodesic flow of a hyperbolic three manifolds has an excess of invariant two forms. So besides the usual contact form d alpha has an additional one lurking in there that only happens in dimension 3 and for the hyperbolic metric. So the kind of philosophy was, well, if you move out of this thing which is very nice and has a sort of excess of invariant orbits, you would expect that thing to drop. And that's exactly what we ended up proving. Okay, but now the point of view that I took a little bit after that is that this was too conservative. You want to dissipate, so you would really like to understand the Anosov flows that do not preserve a volume form. And this is the actual generic picture. So the real world is not the comfy contact world, but the real world is you don't have any volume form being actually preserved. So what's going on in this sort of case? So you see, one sort of begins with the order of vanishing at zero, but then you understand these resonant forms, and then what you kind of get the feeling that what you really want to understand are these sort of invariant objects, and then that has this nice consequence of the real zeta function. But the really kind of a structural thing that you care about are these resonant forms. Okay, so this is where I can put my foot on the gas, I guess. So Anosov flow, everyone knows what this is, so I don't need to sort of tell you. Just for the sake of notation, I call E0 EUS, just a splitting. Basic example, negative curvature, we don't know this. You can ignore this picture, this is just a kind of usual picture that I have. People have never seen this before. We can move on. And then, in the microlocal approach, the sort of immediate thing to do is you go to the cotangent bundle and you dualize the splitting. Yeah? So I call E0 star what kills EU plus ES, EU star what kills E0 plus EU, and ES star what kills E0 plus ES. So this, just this very trivial thing to do has already one consequence, which I want to point out. I mean, this is all very easy, but I think from a conceptual point of view, it is important. These guys, EU star and ES star, are not sensitive to time changes, because they only depend on the weak bundles. So a couple of basic properties. If you make a time change of an Anosov flow, you get another Anosov flow. And the weak bundles do not change. It's been known for ages. But this is only, only depends on the weak bundles. So this EU star only depends in principle on the foliation, not on the actual way you travel. Very trivial observation, but kind of important. Now what I want to do is look at the space of distributions with values on K forms where I have the wavefront set placed in the right place. So I want the wavefront set of my distributions to be in EU star. That's the notation. So let me just, for the benefit of, a lot of people, most in the audience know the wavefront set. My apologies, there may be one or two that might want to be reminded quickly about what the wavefront set is. So essentially you try to capture the directions in phase space in which a distribution is or is not a smooth function, and the way you do that is you first say what is not in the wavefront set, and the basic idea is very simple. You kind of localize, you multiply by a function that is not zero at the point, look at the Fourier transform, and you say that you're not in the wavefront set when you have rapid decay in a little conical neighborhood. So that's the wavefront set. You can move that to manifolds after doing some work you don't worry about. And the example to sort of keep in mind, I guess, the usual classical thing, you take some domain with boundary, and then you take the function that is 1 in the set and 0 outside, and then you can clearly see that the direction in which you jump the most is in the transverse direction. So the wavefront set is given by the conormal boundary to the boundary. Okay? That's the example to have in mind. Okay. So here they come the invariant objects. So these are the guys that I want to understand. So bear with me because there's a little bit of notation here. So essentially, I want to look at distributions with values in forms. So if you want to have a picture in your mind, locally think of the usual basis of forms, the x1, the xk, and you write your form as sort of linear combination of that, but the coefficients are distributions now. And those distributions, I ask them to have wavefront set in EU star. Very specific, yeah? Okay, fine. And now, the operator that I want is the Lie derivative. That is the guy that makes this invariant. And in principle, I'm not just interested in just applying the Lie derivative, but I want powers of the Lie derivative. So that's the sort of Lx to the power of L. And so these resonant forms with index KL are essentially, I apply the Lie derivative L times, and I get equal to 0, but always asking my U's to have wavefront set in EU star. And the other thing that carries a lot of information, particularly for the world zeta function, is a subset of these, which is very important, which is, in addition, forms which are killed by the vector field. When you contract the form with x, you get equal to 0. So we put a little 0 here to sort of denote those. Okay? And now I can pack all of this by taking the union in L, all the powers of the Lie derivative. So I call this ratio k infinity, and the dimension of that, which I'll tell you in a minute that it has to be finite, I call that mk0 infinity, and this is what we call the algebraic multiplicity for the Lie derivative, essentially, because you're looking at powers of this. Okay, And then when L is equal to 1, I call that res k0, and similarly, if I don't contract with X, I call that res k1, and the dimensions of that are the geometric multiplicities, because you're just looking at the linear map being applied once. Yeah? And then comes the following important definition. I'm going to be mostly interested in the action of the Lie derivative on the kernel of Ix, which is a contraction with X, and we call this semi-simple, that action semi-simple, if there is an agreement between the big guys and the little guys. So basically, you want the same algebraic and geometric multiplicity. Yeah? And this is exactly what you ask in linear algebra, I guess, for a map to be semi-simple. Okay, so these are the objects that I'm interested in, and the reason why these spaces are finite dimensional, well, this is exactly all this business with the anisotropic Sobolev spaces. So you can construct a very good Lyapunov function for the symplectic lift of the action of X, and by choosing that function carefully, you can make the Lie derivative become a Fredholm operator, and all these things become finite dimensional, and all of a sudden you have a very nice spectral theory, and at the end the resonant objects do not depend on the Sobolev degree that you have picked, and then you can capture the whole thing just placing the wavefront set in EU star, which is, I think, is kind of wonderful. So it gives you a really kind of conceptual way to sort of put these things. So this is wonderful. This, there is sort of earlier work by a bunch of people, very important earlier work. Again, one has to be sorry if I left anyone out here, but there was sort of in some sense, very similar attempt at looking at these anisotropic Sobolev spaces. But again, I think my preference is to use the microlocal point of view. So I like this thing placing the wavefront set. Very nice from a conceptual point of view. Okay, and now what is the relation between the Well zeta function and these dimensions? Well, there is a Well factorization formula essentially that allows you to factorize the Well zeta function as product of 3 other functions and the zeros of those functions. The order of vanishing at 0 of those functions are exactly given by these algebraic multiplicities added in this alternating form. Yeah? So if you know how to compute these guys, then you know the order of vanishing at 0. Computing these guys for higher powers of the Lie derivative is kind of tough, but you might hope to actually compute the dimension of the geometric multiplicities. So this would be the kind of relevant objects, and then hope for some form of semi-simplicity that you can prove. So then these things are the same, and then you end up computing the order of vanishing at 0.
Is there a corresponding formula in higher dimensions?
Yes. Yes. So everything works here in general in higher dimensions for any Anosov flow, and this was well understood by all these people. So here I'm not claiming anything, any sort of innovation. Okay. So what is the challenge then? Well, really, there are a couple of things you can do very quickly. It's very easy to check semi-simplicity for 0 forms and for 2 forms. I mean, the fact that you're working in dimension 3 helps you a lot, obviously. And you can also really check that these have dimension 1. You can think these are actually spanned by the constants. I'll tell you in a minute what actually spans this. The real challenge really ends up being, and then we knew quite a long time ago, is that you have to understand really 1 forms and semi-simplicity for 1 form. So you would really like to compute this geometric multiplicity and ask yourself whether you have some simplicity for k equal to 1. Again, once you go to higher dimensions, there is a sort of similar thing for other sets of forms. Of course, it gets harder. And so let's stay in dimension 3. That's a real challenge. But once you step out of the volume-preserving world, there is a kind of nice new, well, not a new guy, but a kind of replacement of the volume form. And we saw yesterday, these are the Sinai-Bowen-Royal measures, which are great. And the resonant 3 forms are actually spanned by the unique, so I'm going to assume in a minute, or maybe I will say it now, just in case I actually forget. My Anosov flows will always be transitive, so I'm not thinking about anomalous things, just transitive guys, you know, normal guys. And in that case, there's just a unique SRB measure, and this actually turns out to be a resonant 3 form. So I'm just going to maybe, yeah, tell you a little bit and spend just a little bit of time about this. There is this sort of, so yesterday we saw 3 different ways of looking at the SRB measure: equilibrium, state, physical measure, weak limit of the volume form. But I suppose you want to sort of explain to an analyst what the SRB measure is. So a PDE guy. Well, you can begin with this, which is great, I think. So the SRB measure is the unique invariant probability measure which has wavefront setting U star. So this is essentially comes out of you know, this microlocal point of view, but people in this audience that know better than I do. And in fact, in this work, they do this for higher rank Anosov actions, which is sort of much harder setting, but in, sort of along the way, they take case of the k equal to 1. Right. So, but also what happens once you go out of the volume, the volume preserving case, is that we have 2 SRB measures. There is an SRB measure for x, but there's also an SRB measure for minus x. And these 2 things don't have to be the same. So these are different equilibrium states that, of course, when you preserve volume, they are the same, and they're the same if and only if you preserve volume. Yeah? So you get 2 now, so things bifurcate. And as I said, you can think of this as a measure, or you can think of this as a distributional 3 form. So let me just, again, what I'm going to say is very simple, but coming back to this question, you know, how you would explain what the SRB measure is to a sort of PDE person, I would do the following. I would say, well, you know, I mean, take, let's say you focus on the plus one. So you take a background, nice infinity volume form, anyone you like, yeah, omega, and you just say, well, this is a 3 form, so I will be able to write it by a distribution times this volume form. Well, now this F is now a regular distribution with wavefront setting U star in your manifold. Yeah. And then you just say, well, I want this guy to be invariant, so I just do the lead derivative, and I mean, in case you worry about distributions, all these operations are legal. Yeah. So you have to worry about the distributions when you start taking pearls. Then you really have to pay attention. When you apply vector fields and differential operators, it's all good. So you do this, and so what would you get? Well, this would be x applied to f, omega, plus f times the lead derivative of x applied to omega, and this is the divergence of x with respect to omega times omega. So you get x applied to f plus f times the divergence of x omega times omega. And you want this to be 0. So you get the following transport equation. You get x plus divergence of x with respect to omega being applied to 0, applied to f being equal to 0. Yeah? And if you want to tell a PDE guy what the SRB measure is, you say this. Yeah. So if you don't put this, there are tons of solutions of this. You can prove that actually. Lots of solutions in the distributional sense. The moment you do this, you pinpoint the SRB measure. Okay. So, now we get into the thing that I was talking about yesterday. So, now we do, you know, you can contract the SRB 3 forms with X, and you get a nice volume form, W plus W minus, which is also invariant, and these forms are closed. And therefore they have a class. They have a class in H2. this is very easy to check. That is actually Poincaré dual to what is called the winding cycle. So the winding cycles are these things that were actually introduced by Schwarzman, 50s, that you can attach to any invariant measure. You can attach a class in H1, but this is also a dual point of view, which you can actually see them as classes in H2, which is the point of view that I want to take. Yeah? But it's the same thing. I'm not doing anything that hasn't been seen before, right? Okay, so I have these classes, these asymptotic cycles, and this, so maybe this, oops. These are going to play, these classes are going to play a key role, but there's one additional quantity that will be very relevant, and this is related to the helicity that I was talking about yesterday, which can be defined in this case. So let me sort of tell you quickly how you would do it, yeah, when you're not preserving volume. So for that, you would need the two winding cycles of the SRV measure to vanish. So suppose the two winding cycles of the SRV measure vanish, then you have two primitives. Yeah? Two primitives, tau plus and tau minus, and it's very easy to check that you can pick the primitives with a correct wavefront set. Yeah? So for the plus in U star and for the minus in E star. And now, and this is where I think, maybe you have to pay attention for a moment, you do this kind of slightly dangerous thing when you multiply two distributions, right? But life is good here, because you have the correct wavefront set condition, and the Homander classical theorem will tell you that this is legal. Yeah?
Sorry, how do you know that the wavefront set of tau plus is in EU?
You can construct a primitive where the wavefront set has that property.
I mean, use the Hodge decomposition theorem and show that it tells you this.
No, but about the wavefront set, I mean, the Hodge decomposition.
Yeah, it gives you that, yeah.
A couple of things going on here, because you have two things now, so you get two of these integrals. You can check that they are the same by Stokes' theorem. Of course, you can ask me now, I guess you're probably thinking, what about if one is 0 and the other is non-zero? Well, you can still define one, but then it might depend on the winding cycle of the other one. So you can write down a formula, but it's not independent of the primitive. There is a class that you have to carry around. So the kind of best quantity is when you have both winding cycles equal to 0, and this pairing kind of works wonderfully. And I think this is the thing that generalizes the classical helicity for the volume preserving and also volume preserving flows in general for the Anosov case, the SRV measure. Great. And here's the question again, but easier. Right? So the question that I asked last night was, volume preserving Anosov flow with zero helicity. Now I'm asking something a little bit easier. Do you know any Anosov flow for which this helicity is equal to 0? Which, you have a larger class, so you might be able to sort of catch something there. Maybe, I don't know. But technically, this question is easier than the one last night. Okay. I think I won't say any more about the helicity, sort of except how it affects the resonant forms, but maybe just sort of quickly. We do actually prove that the helicity is essentially a sort of suitable integral of a linking form with respect to the two SRV measures, and we also prove, and for this we use recent work of Coles and Sharp, that you can also capture this number by some asymptotic linking number of closed orbits as you move along. So we have these sort of interpretations. This is sort of quite natural. Okay, so just to summarize the three quantities, the two winding cycles, and then when the two are 0, the helicity. Okay, so here is the core result. So I'm not going to rush on this, so take time, a little bit of time. Okay. So basically, this tells you everything you ever wanted to know about geometric multiplicities in terms of these three commanding quantities. Yeah. So the table here, so just take X, a transitive Anosov flow, any transitive Anosov flow, and the geometric multiplicities are all commanded by these two classes and the actual helicity. And this sort of table here tells you on the left a little bit more information. It tells you the resonant forms at 0. Okay, so maybe just to sort of clarify, when I say resonant forms at 0, because I'm thinking of the Lie derivative, things in the kernel of the Lie derivative. You could ask whether you have other resonant forms for other eigenvalues. I'm not saying anything about that. I haven't even looked at that, right? But then there's this other zero coming from the fact that I'm actually contracting my theta. And just in case anyone is wondering about the relation with this, with the work by Gabriel and Viet, that relates, they have like a correspondence with the RAM complex. Well, in their case, really the guy that comes into play is more or less this one, res1, not res0. But then, as I pointed out to you, the res0 is the one that commands the order of vanishing of the Rho zeta function. So, okay, and this sort of tells you how these sort of dimensions change as you do different things with the winding cycles. Yeah, these are all the sort of possible cases. So you see changes, subtle changes in the actual dimension of P1. So here you see this sort of drop by 1 when you have non-zero winding classes. There is this really rather curious, these two rather curious case. This is particularly curious. You know, you can go from this to the other one just by flipping x to minus x. So this is a bit of an illusion. So these two columns should be actually one column. But the symmetry is, you know, you have to be careful with the symmetry. But for example, what happens here in this sort of column is that resonant forms at 0, you end up picking up one guy that is not closed. So something that you don't see in the volume preserving case, neither in the Dyatlov Swarovski case. You get an invariant object there popping out that is not closed, which is rather curious. So then the theorem by Dyatlov and Swarovski, in some sense, has been reduced to this entry. I'm sure they don't like me saying that. I have reduced it to one entry in the table. And then, of course, the question with zero helicity is that I would like to know if these things exist or not. Which is also a little bit curious because this, in the zero helicity case, you end up picking up an extra sort of additional form.
But, sorry, in the second or third column, yes, do you have example where you have Anosov flow with omega plus not 0 and omega minus?
Thank you, Gabriel. This is, I love these examples, in fact, and I will get to that. You might see me kind of excited when I talk about them, yes. So, in fact, what I want to do next is give you examples of everything, except, unfortunately, the zero helicity case, which eludes me. Okay. Okay, so are you happy with the table? Maybe there's no need to kind of remember, really. I don't remember. The sort of important thing is that the three quantities kind of command the thing, and these are kind of, you know, we want to understand these sort of winding cycles and these helicities and so on. And, you know, it takes a little bit of work to sort this out. Kind of. Okay, and then there's some sort of additional little bit of information here if you want to see exactly what the relation with the topology is. Okay. Now, here's a little bit of a summary of the sort of examples, and I guess the kind of picture that maybe you want to have in mind. Yeah? So it turns out that these functions, the winding cycles and the helicity, are actually very nice, and you can differentiate them and compute the first variation. Yeah? And you can actually show that the kind of local geometry of these things looks like in the picture. So imagine you're in the world of all the world of Anosov flows. So the kind of picture looks like this. The places where the winding cycle is actually equal to 0 in one or the other are essentially some finite codimensions submanifolds of the space of all Anosov flows. So you have these sort of they're not exactly hypersurfaces, they have to do with B1. But these sort of, you know, finite codimension objects that kind of look like this, and they sort of intersect sort of quite nicely in one of the columns, which is sort of red line, where the two winding cycles are equal to 0. And it is in that red line where you can define helicity. So inside that red line, the helicity equal to 0, actually we can prove, even though we don't know if the inverse set of 0 of the helicity is empty or not, but if it were not empty, it would be a nice codimension 1 submanifold of the red line. Yeah? So, but we don't know if that guy exists. So in that red line, there's also quite a lot of excitement, well, a little bit of excitement here. So x0, let's say, would be the usual geodesic flow. This is where I guess most of us have spent most of our lives. We've been very comfy with. I'll tell you in a minute about these fascinating quasi-Fuchsian flows that were introduced by Gis, and I think they have been kind of forgotten a little bit, unless someone tells me otherwise, but I think it's a marvelous class. And then the point about and quasi-Fuchsian flows, which are very interesting objects, and here, coming back to Gabriel's question, there are these sort of beautiful examples in which you can have sort of an Anosov flow with one weak foliation being infinity, but the other is not. Yeah, you don't see this in the contact. And these guys land here. Yeah? But the generic picture is a guy like that, right? Which is both winding cycles different from zero. And, you know, well, I can tell you, if you're a geometer, you would like to find a geometric guy there. Well, this actually, you can kind of catch those guys by doing geodesic flows of affine connections, but with torsion. So you put torsion, the limited symmetric torsion, but the moment you put torsion in your affine connection, you dissipate, and you can prove that for that class, you catch guys with different winding cycles. Okay, so kind of satisfying. I would say, you know, I would have been completely happy, sort of except for that sort of mystery equal to zero. Okay, so,
Is there something corresponding to x infinity, but with s and u interchanged, a dot somewhere in the other leaf?
yes, yes. Yeah, you just do minus x.
Does
And you flip to the other leaf.
it have a name? Or?
In fact, the name quasi-Fuchsian, so I think Gis christened them quasi-Fuchsians, and you know, the people that work really on quasi-Fuchsian groups, and they don't know why we call them quasi-Fuchsian, but there is a reason. Because it's like pairing almost two Fuchsian groups. So that's the only ones that I know have names. The other ones, you know, I don't know, people don't look at them maybe too much. Okay, so I think I'll spend the last few minutes that I have getting into a little bit more detail on the examples. Okay, so to give you examples of this, my sort of, oops, that's horrible. One should not reveal the excitement coming up. To tell you, so we have basically a different approach to quasi-Fuchsian flows, which is, again, more a PDE approach. But not that I don't like Gis's approach, but, you know, if you want to do computations, you want, you know, it's better to have a PDE approach, I think. And here you want to compute resonant forms. So let me tell you about this sort of kind of fascinating class of examples. So these are connected with what's called the coupled vortex equations that come from physics. And you do the following. You take a closed surface of high genus with negative curvature. Or maybe, you know, you don't even worry about the curvature of G for the moment. And you take a differential of order m. So namely, this is a, you know, a section of the nth power of the canonical line bundle. Or something that looks like a function times dz to the m, where your coordinate dz is the one that comes locally from the fact that the metric G makes your surface a ripple. All these different ways. Okay. The coupled vortex equations pairs a metric with a holomorphic, with this as a differential. First equation, very simple. You have a holomorphic differential. Yeah? These are very relevant objects. We all like them very much. And there is the coupling. So the coupling comes in terms of the curvature of the metric and the norm of the holomorphic differential. Yeah? It depends on the actual degree. So this gets interesting only for m greater than or equal than 2. Yeah? So these are the coupled vortex equations. And the coupled vortex equations can always be solved. So the coupled vortex equations can always be solved if you give the conformal class of G and and you give a holomorphic differential. You can always find a metric in the conformal class satisfying the second equation by essentially solving a nonlinear, but you know, mildly nonlinear. It's a being quasi-linear, I think. It's really PD. So kind of nice class. And here's the nice thing, that if you take the holomorphic differential, but you look at, let's say, the real, or I did it here with the imaginary part. So you can think of this A as a symmetric M tensor essentially. And then you input different entries, you just input V, 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 M times. So this gives you a function in the unit tangent bundle of your metric. Yeah? And by taking real or imaginary part, doesn't matter what you do, you get a nice function lambda that, the way to think about this is that you have polynomial dependence on V, where the degree of the polynomial is essentially M. And then you look at the following vector field. You take the geodesic vector field and then you do this vertical perturbation, plus lambda B. So yesterday I talked about doing x0 plus SV. Well, I'm doing here something a little bit more sophisticated, kind of putting there a lambda that comes from a holomorphic differential of order M. And the result, which, okay, is not hard, but, it's not really on the surface. It's not like, for the geodesic flow. You have to kind of work a little bit. Is that the vector field of that is always Anosov. And even better, this is very nice, it dissipates. So when I say it dissipates, it means that the flow does not preserve an absolutely continuous measure. There's no volume form being preserved. So you're really in the case of two SRB measures. It dissipates if and only if the holomorphic differential is not zero. Yeah? Of course, if the differential is zero, then you're back in the hyperbolic case. Okay, so that's a nice class, and within that class, there's lots of things. So the cases m equal 2 and m equal 3 being particularly relevant. So I'll talk about m equal 2, m equals 3, but just to mention quickly in case I run out of time, m equals 3 is really closely related with what Mark talked about in his lecture that he called D. And this is essentially connected, it's essentially the Hilbert geodesic flow that is related with flat representations on SL3R. So you kind of know that you are in a kind of good territory. M equals to 2. Well, this is the quasi-Fuchsian flow. This is really not the way it just defines the flows. He did a complicated construction and ended up constructing the flow by changing the smooth structure on the three manifold. Yeah? He constructed first sort of charts. The charts were homeomorphisms, and then put a smooth structure on the manifold, and then used the fact that three manifolds have only one smooth structure, and using that he constructed the flow. Well, good luck if you want to compute anything after you have used a theorem that tells you that three manifolds all have the same smooth structure. So you want a different approach. And I think, one thing that we can prove is that with this way we catch all these quasi-Fuchsian flows. I cannot resist telling you about it. So let's say you ask me, what is the analog of the great thing that we all love, PSL2R divided by R in constant curvature, but in the world that you dissipate? What is the simple dissipative flow? And why are these guys remarkable? I'll tell you in a minute, that you can come up with these guys. These guys have the remarkable property that the weak bundles are C-infinity. So you can see why Gis was interested in this. He was trying to classify, and he did classify, all transitive and also flows whose weak bundles are C-infinity. And these were his models for non-homogeneous dynamics. But they are kind of algebraic, right? Because they are associated with a quadratic differential. But it's a nice class, and he parameterized that essentially by 2 points in Teichmuller. Teichmuller terms itself. Here what we're doing is parameterizing by cotangent bundle of Teichmuller. One conformal class, one holomorphic quadratic differential, which is a cotangent element. And you have to show that these two things are the same. This is non-trivial, but they are, basically. Okay, so if you really ever have any need to have, what is the kind of real class that you have to understand if you want to understand anything in a non-dissipative setting, this is. And for these guys, we can compute everything, leaving one little problem, which is annoying that I will tell you. But in particular, we can compute the helicity, we end up proving that it's actually positive, in terms of various relevant quantities. So what are the relevant quantities? Well, volume, you would expect volume to pop up in a reasonable place with a suitable normalization. And then there are two additional things. One wonderful quantity that you tend not to see in the volume preserving is the disentropy production that was introduced by Rell. Yeah? And Rell was very keen in these systems that dissipate. And the entropy production, you essentially integrate the divergence. So V lambda ends up being the divergence of the vector fields against the SRB measure. And it is a result of Rell, basically, that this entropy production is always greater than or equal to 0 and positive if and only if the flow dissipates, so there's no volume preserved, no volume form being preserved. So this guy is positive, so you get a sign, and then there's a little bit coming out of the geometry. You need a solution to this transport problem, the unique Hurley solution that solves this. So this V is the vertical vector field, and you need to sort of pick that. And that's a formula that you get for the helicity. Kind of, I don't know. I mean, this is what you would expect, right? If you make the case that these quasi-Fuchsian flows are, like, you know, such an important class, you would hope to sort of be able to compute that, but it takes some effort to compute that. So. Okay. And then the thing with semi-simplicity, have to speed up a little bit. The thing with semi-simplicity, well, you know, these quasi-Fuchsian flows, the way I have defined them, they come up with their own parametrization. Unfortunately, for the actual parametrization, we cannot prove that the thing is semi-simple. But we can actually prove that a generic time change of these guys would be semi-simple. And we actually compute all the sort of invariant forms. So if you're in one of these generic time changes and you go back to everything I said, then you end up finding the order of vanishing being exactly like in the geodesic flow case. Yeah? So this would be a case where both winding cycles are zero. Proving that the winding cycles are zero is not an easy thing. Computing these winding cycles takes some effort. But they are zero, and therefore, since they are zero, and if you know semi-simplicity, okay, so a quick thing on time changes. So as I mentioned, time changes do not change any of the resonant forms at zero. So the key property here is semi-simplicity, and there is this conjecture that if we had this conjecture, then we would solve it. Everything would be the end of things. So if I had to say there are two problems here left over, zero helicity, and this thing that we think is true, that if you take, you know, a kind of generic function, generic time change will make it semi-simple. And semi-simplicity is dangerous because we also proved in the previous paper that if you just take constant curvature geodesic flow, you can make a time change so that it's not semi-simple. So there are time changes of constant curvature that will change the order of vanishing of the zeta function by violating the semi-simplicity, not because the resonant forms change, because those do not, but because of a time change. So this is the best thing you can hope for. So that's the conjecture of what we proved. This takes some effort, and it's related to a weird problem about product of distributions, is that this is true for quasi-Fuchsian flows. And this is how we get the previous theorem. Okay, so I think I finished telling you quickly about this geodesic flows with torsion. So here what you do is very similar to these sort of coupled vortex equations, but rather than running this thing with a differential of order m, you run them with a one form. And the way this works is like this. You take your favorite closed one form, and you define lambda to just be essentially the one form on x and v, and you do the similar construction, x0 plus lambda v, and it turns out that these flows were actually considered by Wojtkowski quite a while ago, and then, you know, back in the day, quite a while ago, I proved that these flows actually preserve an absolutely continuous measure if and only if the form is equal to zero. So they dissipate, and that's the reason why actually Wojtkowski was interested in them. They were sort of models of non-equilibrium statistical mechanics. Don't know much about that. That's the way they were thinking about these things. But there is yes. So these are actually reversible, which is quite nice. So you have the usual flip that you see in the geodesic flow that conjugates x with minus x, which gives you a nice additional symmetry, tell you that the classes of the SRB measures are related, one is minus the other. So if one is zero, the other is also, so if one is zero, then obviously the other is zero too. So you cannot have this sort of weird. And you can also see them as the geodesic flows of the unique affine connection that is compatible with G and has this particular form for the torsion, where this is the Hodge Starbright. So those flows, I guess maybe I'll finish telling you what the theorem is. For these flows, you do jump. Yeah? For these flows, you can prove a couple of things. You can prove that the winding cycles are non-zero. You get the symmetry here due to the fact that they're actually reversible. there is a drop in the dimension of the first Petit number, and there is a drop in the order of vanishing at zero for these geodesic flows with torsion, which were sitting, these are the guys that sit on this kind of generic position. Okay, so I think this is a good place to stop.
All right. Are there any questions for Gabriel?
Maybe in this last theorem, the fact that this is an harmonic one form, if you drop this assumption, the theta, you say that it is an...
Yes, so it is, so you're asking whether I can drop the fact that it's harmonic, right?
Yes.
Very likely, we don't know how to prove it. I mean,
But the
so
thing
I
on the
think we have
previous
problems
slide,
there trying to see that the winding cycles are different from zero, if we don't assume harmonic.
things on the previous slide, they were valid without this assumption. On the previous slide, when you say that you have an Anosov flow, if you take...
Yes, so this actually, and also it's just that these winding cycles are very hard to compute. Yeah, so, okay, so I don't like to give problems away because this one I really like to solve myself, but I spend a ridiculous amount of time trying to solve that the winding cycles of the SRB measure of the Hilbert geodesic flow are zero. I haven't been able to yet. You know, it's a geodesic flow of a Finchley metric at the end of the day, but the Finchley metric is just only C1 alpha. It is reversible because it's a cubic differential. It's driving me nuts.
But how much is known about perturbing the original vector field X and then relating W plus or minus to the original X and the perturbed one?
I guess I'd like to sort of answer that by saying you that's exactly what I was trying to say.
That's only the vertical direction. That's only the vertical perturbation, if I understood right.
Ah, well, this is I was trying to give sort of examples, but the picture here is general. So the picture that I have here. Sorry, I misunderstood you. The picture that I have here is totally general. So I guess maybe you're asking if I don't perturb in a vertical direction and I perturb in H. Yeah, actually that's a good one. So to catch these guys, we need to do some, not just X plus a vertical perturbation, but we need to also perturb in the horizontal direction, in the other horizontal direction, in the unit tangent line. Okay. To catch these guys. Yeah, I mean, the thing is that when you put things in the horizontal direction, you don't get any more these sort of connections with geometric objects or things that you kind of like, I guess.
Other questions? So it seems like you have the general picture. So what's the next step now?
Okay, so I offer you two problems already, you know, zero helicity and genericity of semi-simplicity. I really like to compute the winding cycles of Hilbert geodesic flow. I mean, it's looks like an exercise, right?
But there's no hope that, like, you could have such a general, nice table, like for instance on 3D hyperbolic manifolds, or...
In 3D hyperbolic manifolds, we have a similar table, yes. This is exactly what we did with Semyon and so on.
Mm-hmm.
And,
But I mean, you stayed within the world of geodesic flows.
yes. Okay, so you're asking
saying
whether
like
one
if
can
you
do
choose
something
dissipate,
for an also 5 manifolds. Yeah, that's a good question. I haven't thought anything about that.
Mm-hmm.
Stepping out of that with the contact case.
Mm-hmm. Okay, so if there are no further questions, let's thank Gabriel again.